what's going on here. You probably want to go back and process and make sure you got it. Even if you think you got it, you didn't. Go back, right? It's like the local pressure that we discussed versus the systemic pressure. So today we're going to do the journey. Last time we talked about the digestive system. We imagined ourselves as food running through the small intestine. Today will be filtrate and will run through the loops of Henle at some point. And again, this is one of those things that sometimes you get it when we talk about it and sometimes you don't. Add to that the time constraints, which we need to complete. We only have 3 lectures left. So just preparing you and to know that just focus and try to understand whatever you can, and we'll continue. So this is where we left off. We just introduced, we talked about filtration. We talked about the fact that we filtrate almost everything, good and bad, and the idea is to reabsorb the good, right? And we talked about the filtration. We have a filtration membrane, and the membrane itself is, first of all, the cap. The membrane meaning what the filter, what those molecules, the amino acids, the glucose, and the water need to do in order to move from the capillary space inside, from the blood vessel, and going out into the cavity, into the space, right? And later on to the PCTs. So of course the first wall they have to go through are going to be the endothelial cells of the capillaries, and they are very leaky, so that's a very permeable membrane. Then we have other cells that cover this, but again, they form these slits, you can go through them. So what I'm trying to say is that the filtration membrane is not extremely selective. Proteins will not be able to make it, right? But a lot of small molecules will be able to easily do that. And we talked about the fact that pushing everything out of the capillaries, we're talking about the driving force, the blood pressure. And we create that blood pressure by changing the diameter. We have a large diameter for the afferent, for the entrance, and a small diameter for the exit. So we create a great gradient, right, inside that area, inside the nephron. Any questions before we start? Before we complete the story of filtration, but before we start with this. Now I gave you that crazy number, right, of 180 liters per day. So I'm giving you the driving force, and you can see that it's strong. It's about 3 times more than a regular capillary bed, but still, how can we get to 180? So we need to remember 3 things. First of all is the blood pressure. Second of all, what we just said, that the filtration membrane is highly permeable. And the third is that we are looking here at one nephron. But we don't have one nephron, right? We have many of these. If you take all the nephrons and spread them together, they will be larger than our skin. So we have blood pressure in the glomerulus that is high. We have the filtration membrane that is highly permeable, and we have 1.5 to 2 million nephrons. So at the end of all of this, this is how we get so much filtration. We call the filtration rate, we give it a term as the GFR for glomerular. Oh, that's so hard to say for my Israeli accent. It's like saying rule. Glomerular filtration rate. GFR. So much easier. Okay, so much easier. So the GFR is 180 liters per day. If you take all the other capillary beds in our body combined together, that's 4 liters per day. You can see the difference. So filtration is impressive, but we need to keep it somewhat constant, right, in our window. Because if the GFR will be too high, right, per minute, we will not be able to maybe reabsorb everything that we need. We might lose some good stuff. If it's too low, maybe we will not do a good filtration. We will have too much of the waste staying in our capillary. So again, we are in this goal of how to regulate GFR, and that's what we're going to discuss now. So the goal is to keep a give or take constant GFR in different conditions. So let's first of all see what can be challenging in the conditions. So let's go back a bit to the blood pressure. We said this is the driving force. What happens if our systemic blood pressure is, let's say, low. You didn't drink enough, or 20,000 different things happened, and the systemic blood pressure, the big faucet, is now turned down. What can happen to the GFR? Will it go down or up? Let's see if I learn something from the blood pressure story. This is a local, right, pressure. You turn down the big faucet. What happens to the small local parts? Going down or up? Down, right? So if for some reason the systemic blood pressure goes down, the GFR will go down, and then again, the GFR will not be maybe effective. So we have these pretty amazing regulatory systems, and as you can imagine, some of them are going to be intrinsic, depending on the kidney, and some of them are going to be extrinsic, depending on the nervous and the endocrine system, as always, that will keep a constant GFR even when the systemic blood pressure is changing. Now, it's up to some extent because the systemic cannot go too crazy, but we will see that even at the window of 90 to 180 millimeters of mercury of systemic blood pressure, of AMP MAP, we can still keep a constant GFR. We have intrinsic and extrinsic mechanisms. For each of them, we have multiple mechanisms, both intrinsic, both extrinsic. We'll give one example of each. That's the examples. These are the examples you need to know. Okay? Let's start with the intrinsic one, or autoregulation. No involvement of the nervous system, no involvement of the endocrine system. Again, the idea is that this intrinsic regulation can keep a stable GFR in systemic blood pressure of a huge window from 90 all the way to 180. So you're turning either down or up the faucet a lot, you can still make sure that the local pressure in the kidney would be as high as 55 millimeters of mercury. So let's do it together to think what we would expect. Okay? Let's say, for example, that there's a decrease in systemic pressure that we just experienced, right? Would you expect the afferent arteriole to dilate or constrict? Think about it for a little bit with each other, and then we'll talk. What would be the response of the afferent arteriole diameter to fix or to reach homeostasis? Okay, 1, 2, 3. I heard some that said dilate. Okay. Are you okay with explaining? Sure. First of all, what did you say?
I said dilate.
Dilate. The correct answer. Okay. So what? You're in the kitchen, you're trying to wash the dishes, right? And then something happened in the system of the entire chapel hill area, and there's less systemic pressure, right? Less water coming in. What are you going to do? What are you going to do? Turn it up or turn it down? You're going to turn it up. You're going to dilate the diameter. Because the systemic provides now less pressure to the local area, to the nephron, to the glomerulus. Which means that if normally we have 55 millimeters of mercury, if we don't do anything, it might reach 50 or 40 or 35, and that's not great. So what are we going to do? We're going to add more blood from the system into the local area. Do we have any questions on this? Just want to make sure, since most of you said constrict. Yes, Miranda.
So I'm shaken up.
You are one of many, I believe. Okay? Miranda, what's the question?
So the driving force blood pressure, do we need that driving force, the gradient?
We need the driving force here because if it's not such a strong driving force for 55 millimeters of mercury, then there won't be a great enough of a GFR. The filtration will not be as effective. You're washing the dishes with 55 millimeters of mercury. Otherwise, it will not be effective because there's not enough stream, right? It's not going to be strong enough. Now, the water pressure in the system, something happened, a pipe exploded, whatever happened, right? So you have less water. You're saying, okay, my plates are not clean now. I want to clean them. I'm going to turn up the water and increase the local pressure here. How do you turn up the water? You increase the diameter. That's exactly what you do with the afferent. Emma. So the efferent can constrict, but actually we don't change the efferent so much. We keep the efferent kind of constant. What we're going to do is just open the afferent. So we create a greater resistance, a greater gradient inside the nephron, right? And we increase the pressure back to 55. Guess how? Oh, leave that question. That's wonderful, right? A question. Keep that one. So let's see how we do it. Okay? Remember how we call those stretch receptors that tell us the level of the systemic pressure? The baroreceptors. Where are they sitting? In the large arteries, right? The aorta, large elastic arteries, right? We have a similar structure in the afferent arteriole. We don't call them baroreceptors, they're different receptors. But they will stretch when you have a greater systemic pressure, so we have more blood pressure, or they will not stretch, right? They will, and as a result, will change the firing rate when the pressure is lower. So in this example, they will not stretch so much, right? Now, unlike the baroreceptors, they're not going to send any signals to any sort of brain center. This is going to be a local response. We call it the myogenic response. Myogenic, they have stretch receptors in the afferent arteriole, but respond to changes in pressure. If they stretch, if the pressure is high coming in, they will immediately have a local effect constricting that vessel. If, like in our example, they're going to be not stretched, but on the contrary, they're going to relax more than the resting state, that will lead to dilation. That's the myogenic response. So as a result, we have a decreased systemic that will lead pressure. Okay, sorry, decreased systemic will lead to dilation of the afferent, decreased systemic blood pressure will lead to dilation of the afferent arteriole. Larger diameter of the afferent, more blood will flow locally, and then we'll have an adjusted local blood pressure and flow. I think in your printouts, I phrase it a bit differently, and that also works. I talked about resistance, but you can use either of these explanations, whatever works for you, as long as you understand. It's not wrong what you have there. I just thought this rephrasing will help. And of course, everything will be flipped if it was greater systemic blood pressure. Then we will constrict. This will come in. Okay. Abby, ask your question. Ask your question again. We talked about the fact that if we dilate, right? So we had for whatever reason, we had a decrease in the systemic blood pressure, right? And now we fixed it locally. We just dilated pretty big arteriole, right? The afferent arteriole. What's the effect of this dilation on the systemic blood pressure? If we dilate, would that increase or decrease systemic blood pressure? Increase, right? Or decrease? Decrease, right? The opposite. We just change the local is doing the opposite to the systemic. We had lower blood pressure, we just opened more local, so it's going to decrease, the systemic will decrease. So systemically, we just made things worse, right? We had a decrease in systemic blood pressure, we changed it locally, we solved the kidney problem, but we just made the systemic problem worse. Now, systemic, of course, is extremely important and more important than the kidney, but maybe we'll be able to solve this, for example, by constricting other blood vessels, increasing the heart rate, and other things that we learned, right? But there might be a point where we are making it worse and worse and worse until we are crossing a red line, a border. When we're saying, with all due respect to the kidney, we have a problem with the systemic. So now we change our set of priorities. Remember the window between 90 and 180. As long as it's this window of the systemic, that's all good. But what happens if we drop below the 90? Now the body is saying, in other words, with all due respect to your kidney, I'm taking over. That local intrinsic regulation was great with lots of GFR, right? But we have a problem because we don't have a high enough of a systemic blood pressure. And this is when we go into extrinsic. So that's what happens when the systemic blood pressure is too low, for example, below 90. And again, if you flip everything that we'll just say, you can go to above 180. I'm just using the example of decreased and too low. So extrinsic regulation, again, there's more than one example. I'm going to talk about one example. So the goal is to regulate system. Remember, the goal before that was to keep a constant, stable GFR. Now the goal is to keep a stable systemic blood pressure. That's more important. We cross the window, we cross some red lines. So work with each other. What do you think will happen in response? Is it going to be sympathetic, parasympathetic? What neurotransmitters will be involved? Are we going to see constriction, dilation of the afferent arteriole? 3 answers to 3 questions. Talk with each other. They dilate or constrict. Remember the conditions here. 1, 2, 3. I have a whole mix. Okay, I need to hear some explanation. Okay, we'll do it with me. I'll explain and you guys will help me. So that's the local. We are washing the dishes right now, right? We're washing the plates. We had a problem with the systemic, with the city pipes. And now we have less water, so we turned up the water, the tap, right, in the sink. And we're cleaning. But then somebody is calling us and saying, wait a second, you're just making things worse. At this point, the pressure in the city goes so down that we might not have enough water for the entire city. So what are you going to do? Are you going to turn it down, or are you going to open it up even more? You're going to turn it down, right? So are you going to constrict or dilate? You're going to constrict, right? What you're basically saying, oh, I'm going to have dirty plates, but right now, this is a different priority. We're going to have a GFR that is not extremely effective. Probably we'll get rid of some waste, or we will not, or we'll keep some waste, or we'll get rid of the good stuff. That's bad, but it can be so much worse if we just allow the system to go so down. So we're going to constrict. Sympathetic or parasympathetic? Wonderful. Sympathetic, and just neurotransmitters. Nephrine, norepinephrine. Who's going to help the sympathetic nervous system? Adrenal medulla. Okay, everything that we discussed. We see the same concepts. We use the same concepts and the same tools in different systems because they work, so it's great. Norepinephrine and norepinephrine are released by the sympathetic nervous system and the adrenal medulla. Afferent arterioles constrict and filtration is inhibited. It's not going to be blocked, but it's going to slow down. And then we'll have adequate systemic blood pressure to sustain blood flow to the heart and the brain because they are more important right now than the kidney. I cannot tolerate a problem with blood pressure or not enough blood coming to the brain. So much worse than ineffective filtration. This was one example for filtration and regulation, one example of intrinsic and then one example extrinsic. If you got it, you got it. If not, go back and process. That was not the part I was referring to. It's going to become more complicated. Oh, it's fun. It's not that we know. That's how beautiful our sealed body is, right? So, any questions about this before we continue? Okay. So, we talked about filtration taking place here, and now we're going to focus on reabsorption, mainly taking place in the PCTs, and the rest of today's lecture will focus on, we'll talk first about reabsorption in the PCTs, and then what happens in loops of Henle, completing the reabsorption process. Okay? So most reabsorption takes place in the PCTs, the proximal convoluted tubules, and the idea is the PCTs and then the peritubular capillaries that are going to get back the good stuff, right? Okay, I want you to close your laptops, and if you have printouts, just move them aside. And as a given statement, I'm going to tell you the next statement. Assume that the PCTs behave like enterocytes. And reabsorption in the PCTs is similar to absorption in the small intestine, absorption from the lumen of the small intestine. Think together, remind yourself, okay? And in 20 seconds, I'm going to count to 3, and you guys are going to tell me how amino acids and glucose are going to get reabsorbed into the PCTs. When I say PCTs, I mean into the PCT cells, the cells that make up the walls of the PCTs, from the lumen Just the same thing as the small intestine, to the epithelial cells, okay, of the PCTs. Is the question clear? Just based on what we learned about the digestive system. Transport is not enough. 1, 2, 3. Active transport is wonderful, not enough. 1, 2, 3.
Simple.
How do amino acids and glucose are going to move from the lumen of the small intestine into the enterocytes? Specifically, you used that term before, not chaperones, boarders. How do we call this process? Co-transport, right? They're going to take a ride, a hike, on transporters for another molecule. Which molecule is that? Sodium. It's exactly, 100% exactly the same process that happens during absorption of amino acids and glucose from the small intestine. Okay? Open up your laptops again or whatever you have. So here is the tubular lumen, the lumen through which the filtrate runs. Okay, I'm just going to go back just to make sure we got it. So we're talking right now about the arrows here. This is the lumen labeled in yellow. And we're going to talk about the cells that make up the wall. So these are the cells. Here is one of the cells. Here's another. Here's another. Here's the interstitial fluid. And we don't see the capillary, but the capillary will be right here, the peritubular capillaries. In the lumen, what we want is to reabsorb the good stuff, right? Like amino acids. We don't want to lose amino acids. We ate them, we broke the proteins, we want to use them. Now, so we have, if you are an amino acid, for example, you need to pass from the lumen to the cell, out of the cell, and then to the capillary. The easy part will be to the capillary, because these capillaries are low, poor in everything. Remember, they lost so many amino acids and glucose and other nutrients during the filtration process, right? Now they left through the efferent arteriole, and these are the peritubular capillaries. They are looking for amino acids. Everything is low. So whatever you push into the interstitial fluid, that will go easily into the capillaries. The capillaries will probably be what type of capillaries? Fenestrated capillaries, because we want to load as many nutrients as we can possibly do in a given time. So the main challenge will be, just like in absorption in the digestive system, to bring them here. And what we have is what we call that secondary active transport that builds up on transport of sodium. We have sodium transporter, sodium gets in, and sodium is going to be thrown out with a sodium-potassium pump. We call it a secondary active transport because we need energy like any active transport. We don't need direct energy for the sodium or for the amino acids to move in, but we need energy as a secondary part to maintain that gradient so sodium will continue to move. And that's a sodium-potassium pump. So sodium is moving, and now we have the secondary active transport, the co-transport, using symporters, amino acids, glucose, and many other nutrients will use those transporters to move in. Once they are in, they move in through the apical side, they're going to leave typically through facilitated diffusion. So it's not a problem. It's passive diffusion through specific transporters. But the main idea is to bring them in. If we zoom out, okay, this is what we see. Here is one cell, another cell, another cell. Here is the filtrate running in the lumen. Sodium is coming together with glucose, amino acids, some ions, some vitamins, some fat-soluble nutrients will move in. We have some ions, especially anions, that move in between, because we have pi junctions, but it's not a BBB, right? And some small anions can make it through. And again, once everything moved here, I know there's a lot here that is written, but actually if you just think about it, everything will just go into the capillary. What about water? Do we want to reabsorb water that we lost during filtration? Very much so, right? That's 180 liters per day. We cannot lose that, right? We will die in a couple of hours. So how do we, what will happen to the water here in the lumen? What will be the driving force? There's no blood pressure here. There's no blood at all. So what will drive him to be absorbed, or reabsorbed, I should say. Any ideas? Yes?
An osmotic gradient.
Why, how do we get that osmotic gradient?
By changing the amount of ions inside.
Wonderful. The filtrate came in with water and glucose and amino acids and minerals, right? As it goes down, those nutrients, for example, glucose and amino acids, are being reabsorbed, so they are leaving the lumen. So as we continue with the lumen, as the lumen progresses, the solution becomes more, but concentrated or diluted? Diluted. We are losing the solutes because they're going back to the capillaries. So water here has a driving force to move. We either bring back the solutes, and we're not, right, because they're going to the capillaries, or water will follow through, how do we call this process? Osmosis. So the filtrate becomes diluted as it progresses down, the PCTs. Water will also move out of the filtrate. Just give me 1 second. How does water go? What do I ask actually? I always forget. How do water go? How does? I will never get that. Okay. Never mind. So how does the water move? Water is not lipidic, right? And the membrane is lipidic. So what, do we have transporters for water? Yeah. We do, exactly, aquaporins. So we actually have transporters for water. We sometimes don't think about that, but people actually got Nobel Prizes for this, for discovering aquaporins. Mira, they have a question. Okay. So yeah, they're moving through aquaporins and then again to the capillaries and back. This is the basic reabsorption that takes place in the PCTs. This is how we get back the good stuff. If we zoom out even more and look at the entire, almost the entire nephron, let's see what we have. Or if everything went well and we're healthy and we don't have any problems in our kidneys, here we did, number one was filtration, right? We created a filtrate. It ran through the PCTs. We don't see it here, but we have capillaries, the peritubular capillaries coating around all the PCTs. And at the end of the PCTs, before the filtrate goes down to the loops of Henle, here we basically reabsorb all the organic material, amino acids, glucose, and so on. We also absorb about 65 of the water that was filtered, and about 65% of the sodium of the NaCl, which is great, right? That's pretty amazing. But it's not enough, because 65% of the water is just not enough. We will lose too much water in the restroom, and we will not retain enough water. Any questions so far about what happened in the PCTs before we move to the next stop, to the loops, before we start our journey towards the loops of Henle? Nicole.
As the filtrate goes down and the PCT will dilute, why would the water stay?
Water will not stay. Water will leave. But when we say, the one thing we need to remember that can be really confusing when we talk about reabsorption in the kidney, when we say something is leaving, it's leaving the filtrate and it's going to be carried back to our body. Okay? There's a difference between leaving the filtrate. Leaving the filtrate is good when it comes to retaining it in the body. So since you lost, if you look here, you lost from the filtrate. You're now swimming in the filtrate, right? Then you lost amino acids, glucose, different nutrients, right? So it became more and more diluted. Then the water will want to follow, and it will follow. And then it will go to the capillaries and back to the veins and the circulation. Sarah.
So is this way, I guess, how does this system of water reabsorption compare to the lymph flow as water reabsorption?
So the lymph is responsible for everything that happens in the interstitial fluid around the different tissues. Okay? But here we're talking about a whole level, different level of losing water from the capillaries. This is not 10% of the water that was left from the capillaries. This is, again, 180 liters per day. So you cannot just have simply some lymphatic vessels that will keep because they will not be able to retain more. You need a mechanism like we have now to completely reabsorb it. Okay. So 65%. Great. But again, it's not enough. So we ask ourselves, the next goal is how can we obtain more back the water and the sodium? Or in other words, how can we make the filtrate even more concentrated by the filtrate losing water and we are reabsorbing the water? And if there is anything that is maybe the best example that I can think of anatomy dictates physiology and function follows form that I keep on preaching you guys about, it's the next stop, is the loops of Henle. Okay? So the loops of Henle, and specifically the loops of Henle of the juxtamedullary nephrons, and I'll explain what those are in a second. So this is, again, zooming out even more. Here's the kidney, right? And we have the cortex, and we have the medulla, all those rooms, and here's, again, I'm looking at two nephrons here. Here's the cortex and the top. Here's the medulla. And here is one nephron. It was, the coat was removed, so we can see the glomerulus, the PCTs, loops of Henle going down and up, and then going to the DCTs, right, and collecting duct. You guys read about this. We have two types of nephrons. One of them is what we call the cortical nephrons. Why cortical? Because the majority of the nephron is in the cortex. You can also see that the loops of Henle do go into the medulla, but they're pretty short. Well, then we have the other type is what we call the juxtamedullary. Juxta next to. Juxta next to. So that the juxtamedullary, the corpuscle right here is still in the cortex. The PCTs are still in the cortex, but they're much closer to the medulla. And the loops of Henle go down and up from the medulla, but what's the difference? They are much, much longer, and they go much deeper into the medulla, and that's going to be extremely important, that deeper part. And we'll see why later today. About, give or take, 15% of our nephrons are juxtamedullary nephrons. Going to be, again, very important for reabsorption. If you're not a human, but if you're a camel in the desert, what would you expect the percentage to be, lower or higher? Higher, because we need to reabsorb more because we don't have too much water to lose. 100% in the camel or the desert rat, the driest animal on earth, doesn't drink a drop of water, basically, and even the food is solid, then it cannot lose any water. 100% of the nephrons are juxtamedullary, and they go deep, 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 deep inside. Okay. So, to understand how this is going to work, we need to, remind ourselves or learn two things about the system. One of them is more about a reminder, because we talked about osmolality, but we never defined it. Osmolality is the number of solute particles dissolved in 1 kilogram of water. Please note, I'm talking about solutes. This is not sodium, this is not potassium, or this is not glucose. It's all the solutes. We have osmoreceptors that give us information about osmolality, not about the concentration of a given mineral, but of all the solutes. We talked about them when we talked about ADH. We good so far? We use milliosmoles, that's the unit, and basically the osmolality in all our fluids is 300 milliosmoles. And because everything is balanced and everything is equilibrium, that's if you take a drop of blood or a drop of plasma, a drop of interstitial fluid, they will all be 300 milliosmoles, except for one place in your body, and that's the medulla of the kidneys, of the nephrons. So remember osmolality. Go back to that. The second thing that it's not reminding you, because we didn't learn about this, is permeability. We talked about filtration, and then we talked about the PCTs. The PCTs are, throughout the PCTs, they are highly permeable to glucose and amino acids and sodium and all of these, and it's all uniform. The permeability of this region at the end of the PCT is exactly the same as in the middle or the beginning. But when it comes to the loops of Henle, we have a different status or a different case. We have the descending, the going down, the descending arm of the loops of Henle, and the ascending. The descending loop, the cells that make up the wall of the descending loop are permeable to water, but they are not permeable to ions. I will use the term ions. When I talk about ions, I actually talk about NaCl because that's the main thing we want to reabsorb. When I talk about NaCl, the challenge is really just with Na. Cl will follow Na. You reabsorb the molecule of Na, Cl will follow through. Okay? So the descending loop are not permeable. They actually are partially permeable, but for simplicity, we'll just say not permeable at all. The ascending loop, exactly the opposite, a mirror image. They are permeable to ions, they are not, they're impermeable completely to water. The osmolality, the fact that we are going down and then we're going up. The fact that those loops see around them the same interstitial fluid, because they're really close to each other, and that non-uniform permeability, all of these give us the amazing ability to do what we see is going to happen next. Any questions before we start our journey in the filtrates? Okay. So let's see what we have in the interstitial fluid. This is the cortex, and here you have all the medulla, right? And you have the example of a nephron where the loops of Henle are dipped into the nephron. This is not air. This is water. This is interstitial fluid filling up this pool. In the cortex, if we measure osmolality, it will be 300 milliosmoles like any other place in the body. But if you take a sample from different parts of the medulla, it will not be 300 milliosmoles. Moreover, the deeper you take the sample from, the deeper you go into the medulla, the more concentrated, the saltier it is. So we have a medullary gradient of osmolality. It's not 300, 300, 300, it's a gradient, right? Going to the more concentrated. At the bottom is 1200 milliosmoles. That's saltier than seawater. That's extremely, extremely saltier. Okay? The deeper you go into the medulla, the greater the osmolality in the interstitial fluid. These are kind of like the given. How we create that gradient, I'm not going to talk about. Maybe if I have time, I'll say a word about this, but you are not responsible for this. Just take it as a given, okay? Dr. Schimmer created that medulla, as far as you're concerned. Again, I'll say a word about this at the end of the journey, but not critical for this course. Okay. Let's start our journey. Now, you are part of the filtrate. That's what we're going to do. We're going to swim in the filtrate, right? We filtered, and then when we started, we said we had about 300 milliosmoles. And we still have 300 milliosmoles before, when we leave, before we go into the loops of Henle. What about what we contain? If I take a sample from the end of the PCT, from the filtrate, and the sample from here, do they contain the same molecules, the same contents, the same concentrations of contents? Think about it before you nod yes or no. If I take a sample, I'm not talking about osmolality, I'm just saying, okay, what do we have here? How much we have of each? Do we have the same content, the same concentrations? Think about amino acids, for example, or glucose. We use those examples. If I'm measuring levels of glucose here in the beginning of the PCTs and level of glucose here at the end of the PCTs, will those be the same? No, right? Because at the beginning we